Hi, today we're going to really open the door into organic chemistry and tackle probably what's the majority of organic molecules. So I wanted to pull an image from the previous, maybe it was 2 lessons ago, I can't remember, but this is one of the images, I think it was actually 2 lessons ago, one of the images I pulled from the internet to talk about organic compounds as a whole. These are actually all specifically not hydrocarbons. Yes, they all contain carbon and hydrogen, and I guess I should take a minute to talk about this. Every time you see a vertex like this, it's assumed that this is a carbon, and there's a bond to another carbon and a bond to another carbon. That's those two lines you see. And then hidden, they're also just saying, like, we all understand that all carbons make 4 bonds, and there are enough hydrogens there to make that, a satisfied carbon in terms of energetics and stability. This one here would be a carbon that's bonded to 4 other carbons, because there's a carbon, there's a carbon, there's another carbon, and there's another carbon. So this really skeletal way of abbreviating the molecules, it's geared towards, making things easier once you really understand some of the basics of organic chemistry. Really, it makes pictures a little bit easier to understand, puts everyone on a quicker discussion. But that's not what we're talking about today. Today we're talking about things like this, and this, and this, and this, and this. And it goes on. There's all of these all these parts of the molecule. They're called moieties, an atom or group of atoms. They're not carbon, and when they're not carbon, you'll see that the name changes dramatically. The properties change dramatically. The chemical formula is different. The structure is different. So really the big question is, how do we name and classify organic molecules containing elements other than C and H? So what my plan here is with this, we're kind of doing like the surface view, and then my plan is to go into each category a little bit deeper with a different video. This way you guys can view it, at your own pace, at your own leisure. But this is like the surface. We're going to get through what we need to get through to understand and use what we have. So as a door into this, I want to make a comparison. This is C2H6, and we call this one ethane based on what we've learned before, and here are the properties of ethane. We know the structure of ethane, we can draw it, that's what it looks like, but there are 2 isomers of the compound that has the molecular formula C2H6O, and this isn't even empirical. Oh my god, I'm messing up. This should be molecular. But if that's your molecular formula, there are 2 isomers. I think this is a good opportunity to let people experiment and try and draw it, remembering that our rules of 4 bonds to carbon, 1 bond to hydrogen, and 2 bonds to oxygen. Try and figure out what those 2 structures are. We'll just start with that. Okay, hopefully you got to draw at least something. Obviously you hit the pause button if you needed to. But clearly we have 2 different compounds. They have the same molecular formula, different boiling and melting points, different properties, chemical properties, reaction with sodium. Whether or not you know which one's which, we could at least draw the 2 of them. Now hopefully you drew something that looks like this. And then for the other one, you could have drawn this. Or you could have drawn... Oh, oops. Erase. Or you could have drawn maybe this. And keep in mind, wherever you draw that OH, if it's on like the first carbon or the second carbon, it can be in any position. So these 2 molecules, the first one and the third one I drew, of course, these are the exact same. And also, these 2 are also the same because all we did was rotate the molecule 180 degrees. And you can do that, and that doesn't make it the two isomers, they're just the same compound. So we'll say that this is compound 1 and this is compound 2 for the sake of argument. Again, I don't know which one's which, but I'm pretty sure one of the two in that table is 1 and one of the others is 2. And the big difference here is now we've got an oxygen. An oxygen has been put into our compound somewhere, and so like, what are these molecules? How do they work? Maybe you have some familiarity with one or both of them. But the way we're going to address this in our class is we're going to use our reference table and look at table R. It is a humongous table. It takes the entire page, and it labels what we call functional groups. And functional groups are groups of atoms in organic molecules that include things other than C and H. Now they can include carbon and hydrogen, but they need to include something that isn't those as well. So what you can say is if we drew that molecule 2, this is not a functional group, and this is a functional group. There might be some argument, if you wanted to, you could try and like say maybe this would constitute a functional group, like the carbon and like the functional group and its associated carbon, but that's, some people do that, some people don't, so that's a bit of a gray area. Typically, when I refer to a functional group, I'm talking about, the part that makes the molecule look different. But as you can see on the table, sometimes that carbon's included. Briefly, we will talk about that, but that's something I want to get into more as we look at, as we do a bit more of a deep dive into each functional group, or I'm going to kind of lump them together to make this a little bit better. Because there is some, well, I'll put it this way, there's some places where they logically go together in my mind. As it says on the bottom, in case you don't get it, we do have this new thing here, R. And for us, R is going to refer to a bonded atom or group of atoms. I'm going to put this out there. R chains have to contain at least one carbon. They have to. If it's just a hydrogen, for example, this alcohol here that we've written, if R was just an H, if it had 0 carbons, that would be water, and water is definitely not an alcohol by all the things that we define an alcohol as. And again, I'm saying an alcohol. There's more than one alcohol. I'll get into that also in the future. You do see like there's all sorts of information here. The functional group given is they're all listed in the second column. Each family of functional groups has a class name, which is kind of like the homologous series where you said these are all alkanes, and then there's a specific alkane. This one is called propane. And similar, like you'd say these are all halides, and this is a specific halide, and it's called 2-chloropropane. And you can see that like there is some similarity in how these guys are named, but I'm going to get to that in a second. Because going back to our now previous slide with our compare and our contrast, we have molecule 1, and that's this. And then we have molecule 2, which is this. Oh my God. I'm having a rough time with this. I keep drawing C's and O's like they're interchangeable, and they're totally not. And so this one, based on what we can see, we're going to call an ether. And this one we're going to call an alco. It didn't draw right away and then it reset. I don't know if that's going to translate on the video. Alcohol. So knowing what we know from previous like chapters and whatnot, we do know that this is ethane. I do know that naming these, they're probably going to have an eth something somewhere in them. And maybe we can look at what we have there, because there's an eth there that's 2 carbons, so that should probably factor in. We'll see. But the question is which one's which. And what I can see here is that the ether seems to be a bit more symmetrical than the alcohol, right? There's the oxygen in the middle of the molecule. The alcohol actually has an OH. This OH here is indicative of hydrogen bonding. So I'm going to guess that with hydrogen bonding comes a higher boiling point, a higher melting point due to more stronger intermolecular forces. So between the two, I'm going to say that this is molecule 2 and this is molecule 1. Now in terms of naming, we're going to take a little bit more time on this slide. In terms of naming, to name these molecules, we're going to follow all of the same rules that we've seen before, if there's any branches, if there's any double bonds, all of that. But then what's nice about table R is that it gives you an example naming, so you can use that to kind of extrapolate what to do. Looking at this first molecule of the alcohol, I see there's 3 carbons, 8 hydrogens, so it's C3H8 with an oxygen. So that is, that's propane. But they don't name it propane, they name it propanol. And so it looks like you just take the E and you turn it to all. Now there is a number here, and it does seem to be that this is a condensed formula. So this OH is attached to that carbon before it, which would be the end carbon if you flip it. So it seems to me that what you do is you change the E to an all and you use a number. Now in this case, since there is only one isomer, we don't need to use the 1, but there are 2 carbons. We would name it ethane. And I'm about to erase 2 letters instead of 1 because I can't pick up my pen. We get rid of the E, and then we put an OL at the end. If you wanted, you could put the 1, but you don't need to, because it is on the first carbon, but there's only 1 carbon to put it on, and there's no other functional groups, there's no other identifying characteristics that would cause it to be called something else. So this is ethanol. So the question is then, what is this? And it says here we've got our naming scheme. I see 3 carbons again, but there's no prop anywhere here. So it seems like in this naming scheme with the ether, I see methyl and ethyl. So we know that's 1 carbon, that's 2, and I see 2 carbons here and 1 there, and it seems to be like there's a division. So looking at this, I can kind of draw the conclusion that the oxygen is in the middle of our carbon chain, as everything shows you, table R and our drawing, and it seems to be that you name both sides of the ether as if they're side chains. So really what I would want to do is I would want to call this a side chain and this a side chain. So the name would be methyl ether. But also we know that if there's 2 of the same side chain, that we don't say the same side chain twice, we just say di. So interestingly, even though I originally said 2 carbons this point to F, and it seems like in the case of ethers, by the example we've given, that's not always going to be how it's named. So there's like this added layer of you really need to know what's going on with the prefixes and the suffixes and what they all mean. But this would be dimethyl ether with the lower boiling point and no reaction with sodium metal. It does turn out that ethane has the lower of all of them because obviously there's a lot less mass going on, right? The oxygen provides a large boost in the mass instead of like 30, we're at like 40 some. So there's more to be seen, but I included the ethane just as a contrast to the alkenes that we've seen before. These alkenes, we said, have really low boiling points, nonpolar molecules, and we see that like there's some other effects with including an oxygen into your molecule. So really quick, I just wanted to go through this, just what information we seem to have on here. It does seem to be the case that many functional groups need a location number, right? We see a 2 here, we see a 1 here, we see a 2 here. Oh, too far. It also seems to be the case that many names change the E to something. That does seem to be the case with propanol or pentanone or propanal or propanoic acid. And it does also seem to be the case with some of these, and this is where I'm really glad you have the examples. Some functional groups must be terminal. And that's because, when I say terminal, I mean it has to occur at the ends of the molecule. And so that seems to be the case. What you can see is for the general formula, where is my pen? There it is. Can't see this orange very well. I hope it's orange. Nope, that's the highlighter. Pen. What seems to be the case is you can look at some of the general formulas like this aldehyde and like this organic acid. And when the general formula includes a carbon before the R chain starts that has 4 things bonded to it, including the R, that means that it kind of has to occur at the end of the molecule. This aldehyde exists because of a double bond to a carbon and a bond to a hydrogen, so that's 3 bonds. The only option to make this molecule continue is that that 4th bond has to be to another carbon, but that also means that this has to occur at the end of a molecule, because if you wanted to put 2 carbons to put it in the middle, you couldn't. You need 3 bonds, and that would be 5, and yeah, math is hard. It does also seem to be the case in some rare instances, as a last note, some must be central. And there's a couple like this ether that has to occur in the middle of a molecule, and then this ketone here that must occur in the middle of a molecule. And you can see that there are 2 R groups. They have R and R prime. What they're getting at is that R and R prime do not have to be the same length. For example, methyl ethyl ether or 2-pentanone, where R is 1 carbon and then R prime is either 2 or 3 carbons. So there's a wealth of information here, and really the best thing that's going to let you guys become familiar with it is practice. But in general, we can actually just kind of summarize things before I let you start practicing on your own. Functional groups are parts of organic molecules containing oxygen, nitrogen, sulfur, phosphorus, chlorine, bromine, iodine, fluorine. That's X is a stand-in for group 17. I'm trying to think of what others there might be. I mean, basically anything that isn't carbon or hydrogen. Functional groups change structural formulas, properties, naming, suffixes. Or sometimes, sorry, I didn't mention this, sometimes in the case of halides, prefixes. So interestingly, halides are named in such a way where it's almost like it's a side chain, which is interesting, but they're the only ones for which that's the case. And then the last thing, really, use table R. It's all there. You just have to read it. You just have to look at it and make sense of it for yourself and follow the examples that are given there. I'm going to, instead of going through the practice in this video, I'm going to upload some practice. I'll give you some separate practice to let you see that and how it works on your own time. Thanks for watching.